Okay. So in case of surfaces, we have complete information about their structure. We will like to see the same kind of interpretation, same kind of description in case of dimension 3. Okay. So let us see what happens in dimension 3. In dimension 3, unfortunately, no such promising description exists. And in fact, Euler characteristic of every closed 3 manifold is 0. So those of you who understand, you can actually prove this fact using Poincare duality and taking some suitable coefficient at the homology level. You can prove this. Okay. So thus, because no such description is available in case of 3 manifold, so it seems that some different approach to study of this structure of 3 manifold is needed. So what do we do in this case? So a general procedure followed to understand these kind of objects is to decompose them into smaller pieces, and it will be more convenient if these smaller pieces or simpler pieces are familiar to us. This is the underlying idea. Now, to accomplish this, we'll look into the substructure of this 3 manifold. So what can be substructures? We will be interested in nice objects which underlie these objects. So they will be either one dimensional or they will be two dimensional. So when they are one dimensional, we will call them curves naturally. And similarly, when they are two dimensional, they are surfaces. These curves are called knots. These curves will be called knots. I will talk about knots a little more. I will show picture rather. And the surfaces we will be interested in will be restricted to sphere, a torus, and the connected sum of all these objects. I will also tell you what is a connected sum. Okay. So, okay. So let us look at one example. One example of a 3 manifold. Now the study we are so much interested in studying 3 manifolds is because of a problem. This study actually evolved to answer a question about sphere in dimension 3. So sphere in dimension 2, when we write x set of all x comma y, x comma y comma z, sorry, such that x square plus y square plus z square is equal to 1. Similarly, we can define S3. S3 will lie in R4. Okay. So this question was popularly earlier known as Poincare conjecture, and now I am calling it Poincare's problem for some reason. So let us consider a construction of S3. We can see circle, we can see the sphere, but how to see S3? S3, because it lies in R4, it is difficult to visualize. So here is one of the ways. So what do? Is take two copies of a solid cube. Now, solid cube will have 6 faces and number these faces by putting these numerals 1 to 6 on these faces. Glue together those sides of the cubes which have the same labeling. So you take two identical pieces of this labeled cube, glue 1 to 1, glue 2 to 2, glue 3 to 3, and so on. In the end, glue 6 to side bearing number 6. This will be 3 sphere. Now, if you are confused, I just want you to visualize that you have two cubes, two identical cubes in your hand, one in right hand, on other one in the left hand, and their sides are numbered 1, 2, 3, 4, 5, 6. Both the cubes, you are actually identifying side label 1 to side label 1, side label 2 to side label 2, etc. The figure, one figure is shown to you, and it is indicating that you have to identify the identically labeled side. Now, why is it is a sphere? If you look at circle, let us start from circle. Just look at a diameter. Look at the diameter and uh, remove two diametrically opposite points from the sphere. What you will get? You will get two intervals, isn't it? These intervals will be arcs. So what you actually do, uh, what you can actually infer from here, that the circle is made up, circle being one dimension is made up of two one-dimensional discs. One-dimensional disc will be a interval. Okay. So two intervals, actually, if you can join on the boundary, you actually get a circle. Similarly, in case of dimension 2, you take two discs and make them into a bowl kind of shape. Take two discs and blow them so that they become, they take shape of a bowl. Okay. And now identify the boundary of the bowl. When you identify the boundary of the bowl, what do you get? You get a sphere. So in case of one dimension, when you are identifying two one-dimensional discs, you are getting circle. In case of two dimension, when you are identifying boundary of two-dimensional discs, you are getting sphere. The same idea carries here in case of S3. What will be three-dimensional balls or three-dimensional discs? Three-dimensional disc will be balls. And what is a solid cube? Solid cube is actually topologically a ball. And what we are doing by the process which I have indicated here is actually we are identifying the boundary. Are you getting my point? Okay, so let us proceed further. Now, the resulting object, as I have mentioned, will be S3. And it was this object about which Poincaré asked whether every simply connected closed three manifold should be homeomorphic to S3. Every simply connected closed three manifold should be homeomorphic to S3. This was the question which was asked. Now, we will take up this question later on further. Look at a three manifold. Uh, I mean, when it is called simply connected. So it will be called simply connected if every simple closed curve, like the curve which is shown in this figure on the left hand side, you can make it smaller, smaller. This process of making it smaller is called shrinking, and you can eventually shrink it to one point which is shown uh, in the extreme right. Okay. So if you can do this with every simple closed curve lying in the manifold will be called simply connected. Okay. Okay. So this was the question which Poincaré asked, and it was called Poincaré conjecture. Okay. Let us have some more examples of three manifolds at hand. It is always advisable that whatever we are studying, we should have some model or um, some examples of those objects about which we are interested in. Here we are trying to understand the structure of three manifolds. So it is good to have some examples. One example we already saw, it is S3, and how it is made. It is made up of two cubes. I mean, one of the ways of making S3 is the procedure just outlined. Now look at another class of example. A knot, I talked about knot earlier. Formally, a knot is an embedding of S1 in R3. R3 is the Euclidean space of dimension 3. Now, S3 is one point compactification of R3. This all of us know. So therefore, the knot can be taken to lie in S3. We can consider the knot to lie in S3. We further visualize a knot in S3 and consider a tubular neighborhood Nk of K. So actually what is being done is consider a knot. Let me show you some. Yeah, look at this. So left hand side and in the middle of this figure are knots. Okay, so let consider these knots to lie in a sphere of dimension 3, or you can consider them to lie in R3. Consider tubular neighborhood. Tubular neighborhood means you can thicken these lines, the lines which are showing, uh, which are actually comprising the knot, you can thicken it. Now, when you uh, make it thick, you will have tube kind of a structure. Okay, so tube kind of a structure. That tube is what is called as tubular neighborhood, Nk of K. Now, what we do is from S3, you remove this tubular neighborhood. Tubular neighborhood means this tube actually remove from S3. It is important to visualize this, that from S3 we are removing this tubular neighborhood, and that will create a place, and the place can be filled by gluing a solid torus with possibly a twist. So you see, if you look at these knots, you can understand what is being said in a better way. Okay, so a tubular neighborhood is being removed and a solid torus is being glued back, and possibly with a twist. So how to understand the gluing of the solid torus? Consider Cartesian product of a disk with an interval. So that will give you a solid cylinder. Okay. Now solid cylinder has two ends where both of them are disks, and you glue both the ends with some twist, with some rotation of one of the disks. So that gluing will actually give you whatever is required here. And this can fill the place created by deleting the tubular neighborhood of the knot. This process has a name. It is called den twist and den filling. The twisting is called den twist and the process is called den filling. And this way, we have a large class of three manifolds. We will have in our hand lot of examples of three manifolds. Okay, so let me just mention in the passing that the two knots on the left are actual knots, and on the right we have something which is known as link. Okay, what is difference between a knot and a link? We have actually two knots together to form a link. You can see there are two circles, they are joining, but here in the first and second figure, if you see, there is only one figure or one string going on together. On the extreme right, the third figure, there are two strings which are entangled with each other. Okay, so let us move further. Now we come to understand another concept which is known as connected sum. We consider a two sphere embedded in a three manifold. Now, what do we do is we consider this as analogous situation when we have a simple closed curve simple closed curve lying in R2. So when we have a simple closed curve lying in R2, we can talk of Jordan curve theorem. Okay, so this actually separates the simple closed curve separates. So similar kind of situation we are creating here in attempt to understand our three manifold. Consider two sphere embedded in three manifold, which is separating. Separating in the sense that if you remove the sphere, then the remaining part is in two pieces, M1 and M2. So naturally, M1 and M2 then will have the two sphere as their boundary, and this boundary can be filled using three balls, giving rise to two closed three manifolds N1 and N2. So when the separating sphere is removed, we will get two manifolds M1 and M2. Naturally, their boundary will be spheres, and in these spheres, we can fill balls to obtain closed manifolds, the manifolds without boundary. Okay. Now we say that M is connected sum of N1 and N2. In this case, we say that M is connected sum of N1 and N2, and write this in this way, that M is connected sum of N1 and N2. Connected sum is actually shown in, it is indicated by a figure. We have two tori, and from torus, we removed a disk, interior of a disk, and identify the boundary. After identifying boundary, we get the figure which is depicted below, and that will be a surface of genus 2. Okay. Now, a three manifold will be called irreducible if every sphere contained in it bounds a three ball. So you see, we started with manifold and looked at separating spheres. We cut the manifold along a sphere and then filled it with solid ball. And we will expect that we go on cutting till there is no separating sphere left. That is what is the situation where we call the manifold to be irreducible. Like for example, the Euclidean space R3 is irreducible. Okay, this, although this requires a proof, but you have to you can also visualize that R3 is irreducible. A connected sum N1 and N2 will be called trivial if either N1 or N2 is a sphere. So that is what I was saying, that after cutting along separating spheres, we will want that we arrive at a situation where the manifold in hand has no spheres, and if at all I take its connected sum, the connected sum will have other component as sphere. In this case, the sphere will be three sphere. Okay, and then we come to a important terminology. This terminology, using this terminology, we call a three manifold to be prime if every connected sum with M will be trivial. That is, if I write M as a connected sum, then the only possibility is that it gets connected to a three sphere. Then the manifold will be called prime. Okay. So what we have done, we wanted to understand the structure of a three manifold, and for that we tried to simplify the manifold by uh, cutting along some substructures, and those substructures currently we are considering as a sphere, cutting along spheres. And when we cut along a sphere, we arrive at a manifold which is prime. Okay. Now, I have used a term irreducible, and we connect these two terms here. So we connect irreducibility and primeness by a proposition that every three manifold except S2 cross S1 is prime if and only if it is irreducible. So primeness and irreducibility are same except in the case of a exceptional manifold, which is S2 cross S1. We will talk about S2 cross S1 in a little while. Okay. So that is M will be prime if and only if it does not contain any essential sphere. What do I mean by essential sphere? That every two sphere in M bounds a bar. So here is a small remark that if you take a subset which is also a manifold lying in S3, it will be irreducible. Okay. So now consider a situation where which is familiar to us, where we have a covering space. So let this P from M to N be a covering of three manifold. It is a result, a standard result, that if M is irreducible, then N is also irreducible. So this result is mentioned because it has a very important application, consequence rather. So it follows from the previous remark that the three manifold which has S3 and R3 as universal coverings are irreducible, because we have seen that S3 and R3 are irreducible, and we use this result about covering to deduce that the covering base space will also be irreducible in case S3 and R3 are universal coverings. Okay. Now what happens to S2 cross S1? So it is not irreducible, because it is important, first of all, that we visualize what is S2 cross S1. So to start with, we can take S2 cross I. I is a closed interval. Just visualize that S2 cross I is an object where at each point of I, you will have a sphere associated. And the two ends will also be spheres. You just glue them together. Glue the two ends corresponding to 0 and 1 of the closed interval. You will get S2 cross S. Now, this space is, you can now visualize that this is not irreducible, since it will contain non-separating two spheres. But it is prime. It is not irreducible, but it is prime. This is only exceptional case. Why it is so? Let us see a small proof. So the proof contains some beautiful topological arguments. Okay. So let us have an idea. So let S be a separating sphere in S2 cross S1. Okay. Suppose that S separates this S2 cross S1 into two pieces, M and N. Then at the fundamental group level, what will happen? We will get Z equal to free product of M1 and fundamental group of M1 and M2. Why it will so happen? Because the fundamental group of, because a sphere is simply connected, and S1, the fundamental group is Z. So therefore, on the left hand side, you will have Z, and on the right hand side, you will have connected sum of M and N. So left hand side will give fundamental group Z, and right hand side will give a free product of two groups, pi 1M and pi 1N. So if this is the situation, because Z is also a free group, so one of pi 1M or pi 1N must be trivial. So let first component, that is pi 1M, be trivial. Then what happens? Pi 1M trivial implies that the manifold M is simply connected. Okay, so fundamental group being trivial will imply that M is simply connected. Now, a copy M dash of M will lift to the universal cover S2 cross R of this manifold S2 cross S1 by lifting property. So then consider S2 cross R to be equal to, this equality is actually in terms of topological arguments. Okay, so topological equivalence S2 cross R can be considered as R3 minus 0 minus origin. Then M dash lies in R3 minus 0. And what we have seen? We have seen that R3 is actually irreducible. So what is boundary? Boundary of M dash is a sphere. So this implies that what will happen is that M dash is a 3 ball. Okay. Okay. So this is the situation about S2 cross S1. So to sum up all these, we obtain an important result about the structure of 3 manifolds. Every 3 manifold decomposes into prime manifolds. So remember that we have in the first slide, we have put some condition on manifolds that they are connected and this and that. Okay. So every 3 manifold decomposes into prime manifolds like this, and this composition is unique up to permutations and adding or removing of copies of S3. So if some of these MIs are spheres, then we can neglect this, and it is unique. This decomposition is unique up to a permutation. Permutation means you can change the place of these factors, MIs. Okay. So this decomposition of M presents us with pieces which do not contain spheres. Now we have got rid of spheres in M. We are trying to make 3 manifold as simpler as possible. But it may, however, contain other surfaces. Still, it may contain other surfaces. This, in some sense, is motivating us to decompose MIs further into pieces which are next simplest surfaces. So what will be next simplest surfaces? And we are restricting to orientable case, orientable surfaces. They are embedded tori. Okay. So before going into decomposition of 3 manifolds which contain torus, let us understand some technical terms. So let S be a properly embedded orientable surface. A compressing disk for S, this is a definition. A compressing disk for S is a disk D contained in M with boundary of D contained in S. That is, the boundary of D is actually D intersection S. Look at this figure. So in manifold, this is a disk, the one shown by dotted lines, it forms a disk, and the picture shown to you is a surface. The boundary of the disk actually intersects with the surface. So that is the compressing disk, such that the boundary of D does not bound a disk in S. You see, this disk could have lied on the surface. It could have lied on the surface, but we do not want that situation. We want that only boundary of the disk should lie in the surface. The procedure called strategy shown in figure is called compression. What will be the procedure is that you take some disk across some small interval, which is called annular neighborhood of this disk, remove this disk, and then cap the remaining part with disks. Okay, so that is what is called compression. That after compression, the Euler characteristic of the manifold will increase. Okay, increase means that in the sense what, that you see Euler characteristic of surfaces is less than equal to if I forget the sphere and torus, then all the orientable surfaces will have Euler characteristic as even -2, -4, -6, -8, etc. like this. Now, Euler characteristic increasing means that the genus is actually decreasing. Okay. So, further, a properly embedded connected orientable surface in 3 manifold with Euler characteristic less than equal to 0. Less than equal to 0 means I am talking about surfaces of genus greater than equal to 1. It will be called compressible if it has a compressing disk, and otherwise it will be called incompressible surface. Okay, the two terminology. If it has a compressing disk, it will be called compressible, otherwise it will be called incompressible. So further, let this S be a properly embedded surface. After a finite number of compressions, S can be transformed into a disjoint union of spheres, disks, and incompressible surfaces. This one can understand this because we have noted that Euler characteristic increases each time we do compression, or that is surgery. Okay. Now looking at the boundary of D as generator of the fundamental group, we can give a criteria for incompressibility in terms of fundamental group. The criteria goes as follows, that S and M, as in hypothesis, if the fundamental group injects into fundamental group of 3 manifold, then S is incompressible. Okay. This why this will happen? Because if it has compressing disk, the loops, if it is not injective, then what will happen is, it means that there are some disks which are compressing, but then those loops which will act as generator of the fundamental group of S must also be trivial, homotopically trivial in the surface, because they form boundary of the disk. Okay, because of that, this condition is that fundamental group must inject into fundamental group of the 3 manifold. Okay. Now we come to our main topic, for which we have done the homework. This is called decomposition along tori. So till now we have understood decomposition of along spheres, and now the next simpler surface is torus, along which we are going to decompose the 3 manifold to make it still simpler. So let us recall that we have actually decomposed manifolds along separating spheres, so that there are no more spheres lying inside no more separating spheres lying inside the manifold. So in some sense, we have made it irreducible. And now irreducible manifolds, although they do not contain separating spheres, they can contain other surfaces, orientable surfaces, and we have talked about compressible and incompressible surfaces. So let us begin here. Decomposing along tori, which are contained inside a ball, or which bound a solid torus, are not interesting for present purposes. They are not interesting for. So we try splitting around incompressible tori. Okay, so we are actually trying to split three manifolds along incompressible tori. In an irreducible manifold, any embedded tori which does not lie in a ball or does not bound a solid torus is incompressible. This is a known result. Splitting along such incompressible tori leads to a decomposition of manifolds, which is known as JSJ decomposition. JSJ actually stands for mathematicians who have studied and brought about this result. Their names are respectively Jacob, Schalen, and Johansson. It is on their name that this result is crescent JSJ decomposition. Now, if M is an irreducible, compact, orientable, etc., three manifold, then there is a collection. The result JSJ decomposition states this, that if M is such a manifold, then there is a collection of disjoint incompressible tori in M, such that if we split the three manifold along the union of these tori, we get pieces, MIs, which are either some special class of manifold, cipher fibered manifold, or atoroidal. So I will tell you what are these. So further, a minimal such collection is unique up to isotopy. So we were talking about a unique decomposition in case of prime manifolds. Here also, we have some result which says that minimal such collection is unique up to isotopy. Okay. So I mentioned ciphered fibered spaces. Let's just get a feel of what are ciphered fibered spaces. Now, all of us can visualize disk cross an interval, closed interval. Okay, we can visualize. You can look at the figure, a small figure given here, D2 cross I. And we can think of this as a stack of intervals, X cross I. So if you fix one point in disk, then you can consider this as a singleton cross I to be made up of these kind of lines. Okay. Now there is also a central interval. The center of the disk will correspond to 0 or O, and we call this a central interval. Consider the sections, the lowest one and the topmost one, D2 cross 0 and D2 cross 1. So if you fix one element of I, that we are calling as section, and if I fix 0 or the end elements 0 and 1, then those will correspond to the section which I am mentioning here, D2 cross 0 and D2 cross 1. Okay. So identifying these using a rotation of D2 means disk, to an angle of 2 pi p by q for some pair of coprime. So these are some technicalities, but what is going on is that I fix this one and I fix the lower one. My mouse is visible or not? Is my mouse visible on this slide? Hello?
Yes, sir.
Yes,
Yes,
sir,
sir.
it is visible.
Okay. So the lower one and the upper one, you just let it be fixed, the lower one. The upper one, you give a twist. You twist the upper one by an angle. Rotate it by an angle. The angle is 2 pi p by q. Okay. So you do that with some conditions. It is given that q has to be greater than or equal to 2 and the integers have to be coprime, and then you identify them. Okay. Now the observation is the following. The central fiber closes to form the circle. So central fiber, the fiber means the stack of which this Cartesian product is composed of. So central fiber, nothing happens to it. It will form a circle. But what will happen to others? The others do not immediately close to form a circle. Rather, they go q times around the central fibers to form a circle. So you see, if you look at this one, the this fiber means this line, because we are twisting, it will go q times around the central fiber. Central fiber, this point and this point will be identified, but in this point, to identify to this point, it will have to go q times around the central circle. Okay, so the central fiber will be called singular fiber, as on deletion of this fiber we would have an actual, some terminology which Professor Khare talked about in his talk, fiber bundle, a version of that. He was talking about tangent bundle. Okay, so this will actually give a fiber bundle. So in this construction, which what we are having a bundle with a singular fiber. Okay, now in a compact cipher fiber space, we can have a finite number of such singular fibers. The base space of fibering is the quotient space of M, obtained by identifying each circle fiber to a point. So just to visualize a cipher fiber space, you just consider it to consisting of this kind of fibering, and there are many singular fibers. Okay, so just have a feel of this, that what are cipher fiber space. One feel is that there are fiberings, lot of fiberings, and the other feel is that there are singular fibers, as I have mentioned to you. Okay, so locally what will happen, that corresponding to this P and Q, you will have one fibering, then you change P and Q, you will have another fibering in the same manifold. So these kind of fibering will be there, and the manifold will be called cipher fiber. So let us come back to this JSJG composition. JSJG composition says that if I cut this 3 manifold along the torus T1, T2, Tn, then the pieces which I get are either cipher fibered or they are orthoidal. Orthoidal means they do not have torus in them. Okay, they will not have torus in them. It is natural because along the torus we are already cutting, so it is natural that we will have to get some pieces as heteroidal. But if there are still some tori, then it is cipher fiber. Okay, so the resulting fibered pieces, now then they can be further split. You can split them further into atoroidal pieces, but the resulting atoroidal pieces will not be unique unless the collection was minimal. These are established results. Okay, now the manifolds MIs will have torus boundary components because we have cut them around torus, so they will have torus boundary components. Unlike the prime decomposition case, when we split along tori, there is no canonical way to fill the resulting boundary components. Because you remember when I gave you example of 3 manifolds in S3, what we did along along tubular neighborhood of a knot, we actually tried to fill a solid torus, and there is no standard way, no canonical way to fill the boundary. Okay, so that is what is being said here. But the natural way to do so is to try to fill this tori with solid torus, as we did in case of example. But there are infinitely many different ways to do this. So it is best to leave these MIs as they are with the boundary torus. Thus, even if we may be interested in closed manifolds, we would be forced to take up manifolds with boundary, whose boundaries are tori. Okay. Now, finally, what happens? is that what we have actually done is we have decomposed along tori, and we are left with understanding those prime manifolds which are atoroidal and not ciphered fiber. For a class of examples of such manifolds, now if you want to take some examples, look at the manifolds M, which fiber over circles with fiber a closed orientable surface of genus greater than equal to 2. You remember the picture where I was showing connected sum of two tori to obtain a double torus surface of genus 2. You can take, we can take the Cartesian product of that that surface with a interval and glue the boundary components with some homeomorphism and of the surface, and we obtain such manifolds. Now you see here what happens is, because we are gluing the surfaces using homeomorphism, so study of homeomorphism of surfaces or similar maps, sometimes we may be interested in gluing the manifold with some more specialized kind of mappings, and those mappings become important uh, because of this reason. So moving further, so such a bundle, this kind of a structure which we are forming by taking Cartesian product, etc., they are called bundles. Generally, they are called bundles. This is determined by a diffeomorphism. Diffeomorphism means homeomorphisms which are differentiable with inverse also being smooth differentiable. F denotes surface, so diffeomorphism from surface to itself. If this diffeomorphism is not isotopic to a, this is some technical term for those who may know this. So diffeomorphisms of finite order. So the case of ciphered fibered spaces or leave invariant some finite collection of disjoint non-trivial circles in the surface, then M is atoroidal and not ciphered fibered space. Such diffeomorphisms are subjects of Thurston's theory of pseudo-Anosov surface diffeomorphism. There is a study of surface diffeomorphisms which are called pseudo-Anosov in Thurston's theory. If you want to take another class of examples, consider the complement of an open tubular neighborhood of a knot in S3, as I have already mentioned. It is an irreducible manifold with torus boundary. It is atoroidal and not ciphered fibered for most of the knots. Okay, so these are some observations about topology. So I think the geometry part which I wanted to do, because I have exhausted one hour, I should do in the next lecture at 2 o'clock. And so for the moment, to conclude, let me just mention that we wanted to study the structure of three manifolds. For that, we looked into simpler substructures into three manifolds. So simpler substructures will be submanifolds excuse me, of dimension 2 and dimension 1. So dimension 1 will correspond to knots, dimension 2 will correspond to sphere and torus and connected sums. So we try to decompose the manifold into simpler pieces about which we are familiar. When we decomposed along spheres, we got prime manifolds, and these prime manifolds may not contain a sphere, but they can contain some other surfaces, some other substructures. So then we try to decompose these manifolds along those simpler pieces, those surfaces. And the most simpler surface was torus, along which we decomposed. And when we decomposed around torus, we got the result which was called JSJ decomposition, Johansen decomposition. And the result was that we got two class of simpler manifolds. One class was Seifert fibered spaces, the another one was atorial. Okay, so this is a I can say a rough conclusion about the geometry of three manifolds which we have been which we have aimed to understand. I hope you have got a feel of some technical things in three manifold theory. Okay, if you have any question, please let me know. Yes, it was too technical, is it? Hmm? Yes, there indeed there is a difference between classroom lecture and online lecture. This time we are confining for some technical reasons. We are confining to online lectures. Maybe sometimes in near future, when we have offline lectures, these things can be dealt with in more detail. Okay. Okay. So we stop here and then we meet at 2 o'clock. Okay.
Thank you. Thank you, Ashish.
Thank you, sir. Sapnil?
It was technical, but you can't help more than this in 1 hour.
Yes. I tried to make it as simple as possible, repeating arguments many times and telling what is going on. And in the flow of this, I might have compromised some precision sometimes, but that was just aimed to give a feel of the topology. Okay.
Yeah. Certainly, you have given a feel of it. What
yes.
is happening?
Yes. Yes.
Geometrically, what is happening?
Yes. So things will become more clear when we touch upon geometry of the three manifolds in next lecture. So because Swapnil is not here, we close the session here and we meet at 2 o'clock for next lecture. Okay.
Thank you. Thank you very much.
Which will be okay, which will be obtained by defining distance between 2 points to be the infimum of lengths of all of the paths between them. Okay, so this is a natural way of defining metric in case of S2. Just a minute, what something has popped up. Okay, now look at projective plane RP2. So we are familiar that projective plane is double covered by S2. Okay, through antipodal map, actually antipodal points you can identify in S2, and thus S2 becomes a double cover of P2. And not only that, it is universal cover because it is simply connected. So the projection map from S2 to P2 has the path lifting property. What is that? That because path is a connected object, therefore it can be lifted to the covering. This is called as path lifting property. So this permits us to define a metric on P2 by defining length of any path in P2 to be equal to the length of the lift in S2. So we will have, if I can draw, let me try to see if I can draw it here. Just a minute. So here it is not a very nice picture. Here I will have S2, and from S2 there will be covering on P2, and from P2 a path, this kind of path will lift, and it will lift into two parts, one in the northern part and one in the southern part. Okay, so this path will lift, and the length, I can measure length here. In case of a sphere, I can measure the length, and that I define the length of P2, the path in P2. That is how we define the length. Okay. Now, this example can serve as a guiding example in our case. So, what we have actually done, look at the previous slide. So, previous slide, we have actually taken a covering space in which the covering had a metric, and using the metric on covering, we actually projected the metric to the base space. Okay, and the antipodal map, this is to be kept in mind, that the antipodal map will be, and because it is an isometry. So the two paths which lifted to P, it may be question before us, it may be a question, genuine question before us, that which of the paths to map to the path. So the paths which we get in S2 by lifting the path in P2, they may have different length, but that is not the case because the antipodal map is isometry. It preserves length. Okay, so both the paths will be having same length. So whatever length I project onto P2, that will work. So this is crucial. This is crucial that it is an isometry. Now this serves as a guiding example for us of a more general situation. The situation is I have a manifold which covers a base manifold N, and the covering is nice covering, which we call as regular covering. M is equipped with a metric, and the covering group is the group of isometries. Okay. So talking about closed surfaces. Now closed surfaces, as all of us know, by up to a scaling, the Euler characteristics of closed surfaces are either positive or zero or negative. Correspondingly, they admit three types of geometry, and these geometry are named as spherical geometry, Euclidean geometry, or hyperbolic geometry, respectively. So in case of spherical geometry, it is positive Euler characteristic. In case of Euclidean, it is zero Euler characteristic, and hyperbolic case, negative Euler characteristic. Okay. So the simply connected models for these geometries, the universal covers we should have, because we are talking in terms of covering space. So simply connected models for these are a sphere. As you know, a sphere is simply connected. We have the Euclidean plane, that is R2, that is also simply connected, and H2 will be the same Euclidean part of the Euclidean plane, but with the last coordinate, we should have greater than 0. That is how we take the hyperbolic plane, the upper half plane. Okay, we say the upper half plane. Okay, so now in general, if X denotes one of these, if X denotes one of these means either S2 or E2 or H2, and if F denotes a closed surface which can be expressed as a quotient of X by a group of isometries G, such that the quotient map is a covering map. Just recall the model. That's why it is important to keep a model at hand. The model was S2 and P2 and the group of covering transformation, which was also isometry. Covering map, we say in this case that F possesses a geometric structure modeled on X. So in case of our model, we will say that RP2, that is the projective plane, possesses spherical geometry, a geometry modeled on S2. Now, it is natural to ask when we are interested in geometry in dimension 3. It is very natural to ask that whether this kind of structure is possible in dimension 3, whether this kind of extension can be had. So some natural analogous objects in this case will be the spherical, the analogy with spherical geometry will be again spherical geometry, which is S3. Analogy with Euclidean geometry will be E3, which is also called elliptic, which is called Euclidean geometry here also. In fact, the spherical geometry is called elliptic geometry, and E3 is called flat geometry, and H3 is hyperbolic geometry in this case as well. So these are spherical, Euclidean, and hyperbolic geometries. Okay. Now we will actually have some history. Till now, what we had talked in previous lecture was about topology of three manifold. We tried to see the structure. We will try to see that whether we can also appeal to geometry, as our experience from 2 dimensions says that since 19th century, we know that geometry and topology are actually complementing each other. Okay, in fact, geometry has given more insight into topology at times. Okay, so to explore this point, that whether similar kind of situation we get in case of three manifolds also, let us see some history. So the history which I am going to elaborate upon is what actually kicked inclusion of geometry in study of topology of three manifold. Okay, that is the point which I am going to address now. Now, the question was originally asked by William Thurston about geometry. Okay, now why did William Thurston come to ask this question? We will present this. We will present some historical account for which we need some terminology. Okay, so let K denote a knot, and we have already seen the space S3 minus K in the previous talk. S3 minus K means from the sphere you remove tubular neighborhood of K. At times it is just written as S3 minus K. Okay. This symbol denotes set theoretic subtraction. Now, the fundamental group, which is denoted by pi k of this space S3K, is called the group of the knot K, or the knot group. In R.H. Fox, as a mathematician who has studied homomorphisms, which are also called representations of this group pi k into the group A5. A5 is the alternating group of degree 5. Permutation groups, all of us are familiar, and this is a subgroup of S5. We know, all of us know, this is quite familiar to us. So R.H. Fox was very much interested in knots, and he studied, for some reason, homomorphisms of knot groups into A5. These are actually called permutation representations of knot group into A5. This will, because we are considering homomorphisms of knot groups into permutations group. Okay. Now, there was a mathematician, named Robert Rayleigh, who became interested with this study, and he tried to classify all A5 representations of the knot group. So in some sense, he tried to study all homomorphisms of the knot group into A5. So you see, I am talking about K. K may be any knot. K may be any general knot, and there are lot of knots. Okay, so this is a general situation. So he tried to study representations. Now here what he did, Robert Rayleigh, he used Fortran programs, and using these programs, he was able to deduce that figure 8 knot complement has hyperbolic structure. So figure 8, let me show you once again the picture of knots which I was showing you in some previous slide. You see, the middle knot actually looks like it is written 8, the middle knot. So this is called figure 8 knot. Because it looks like 8, therefore it is called figure 8 knot. So it was about this knot. Okay. So yes. So he used Fortran programming and was able to deduce that if I confine my K to be figure 8 knot, then the knot group, the complement means this object S3 minus K. S3 minus K had hyperbolic structure. Are you getting my point? Till now, just try to see it from a distance. Distance in the sense that try to visualize. Till now, there was no mention of geometry. I did not appeal to any geometry in case of study of these objects. For example, S3 or the objects like cipher fibered spaces, etc., etc. I never talked about any metric. Now here, out of a study coming from representation of knot group into A5 and Fortran programming, use of Fortran programming, Robert Rayleigh was able to show that the figure 8 knot complement, that is when K is a figure 8 knot, then this object S3 minus K had hyperbolic structure. It's a very important development, very important development. And I believe that till now, before this, Thurston was working on foliations. He was working on foliations, and it was because of this study that uh, this probably made uh, important, I will say, gave important impetus to Thurston to think about role of geometry into topology of three manifolds. From here, the geometry becomes important into the study of topology of three manifolds, where everyone was trying to understand, everyone was trying to answer Poincaré's conjecture. So let me sum it up again. So we had all sorts of manifolds which were all topological. We knew that yes, there is prime decomposition, there is GSD decomposition. All those decompositions we actually boil down to topological manifolds, cipher fibered spaces or heterohedral manifolds. Okay, there was no geometry, but an individual, Robert Rayleigh, is studying S3 minus K, which is which is a topological space. And here, for using Fortran program, the hyperbolic structure was somehow connected with the knot complement, where figure 8 knot was involved. Okay. So now, when K is figure 8 knot, a special kind of representation of the knot group is faithful. Faithful means injective representation, and the orbit space. I am here in these lines. This part is elaborated little bit. The orbit space is actually orbit space turns out to be the hyperbolic space over the image of this knot group into the permutation group, which turns out to be equal to S3 minus K. Okay, so one may be curious that how geometry came into S3 over K. So S3 over K came as a orbit space of this representation. Now, this and some other examples constructed by Rayleigh gave big impetus to Thurston to work on the following theorem. he started working on, on the following theorem. These are not my words. These are actually words of Thurston. Thurston says that Rayleigh's work gave big impetus to me to work on the following theorem. And the theorem is that interior of a compact three-manifold with non-empty boundary has a hyperbolic structure if and only if M is prime, homotopically toroidal, and not a special kind of manifold, which is torus cross I quotiented with Z2. This is a special kind of manifold. Okay. Now, you see, every closed three manifold is obtained from S3 by Dehn surgery along some link. I have already given you example of a link. Now, whose complement is hyperbolic. This is known. These are known things to us. Thurston used computers to study these classes of manifolds. Okay, so Thurston again did some programming and he tried to study these classes of manifold obtained by Dehn surgery. He undertook this study to gain more feelings on how geometries evolve on three manifolds. Are you getting my point? That the study which Thurston, this I have been emphasizing. He got curious and he started exploring that how geometries evolve on three manifolds. So he worked with some examples. Those examples are torus bundles over the circles. Torus bundles over the circle will mean something like you take torus, Cartesian product with circle, and then the two ends you can identify with some homeomorphism, some diffeomorphism, etc. And then it will contain torus naturally, and then perform Dehn surgery along these sections. Those torus will be called sections and perform Dehn surgery along them. Now, with the aid of these programs, Thurston found the pattern of which Dehn surgeries gave rise to hyperbolic manifolds. So he found during his calculations, he found that which Dehn surgeries actually give rise to hyperbolic manifolds. He could then show, so there were Dehn surgeries which did not give rise to hyperbolic manifolds. And Thurston could show by hand that those examples for which the program did not produce hyperbolic structures, in fact, had other geometries. So the pieces which did not have hyperbolic structures actually had other geometries. There were different geometries. Okay. So probably this made him propose the then called geometrization conjecture. So all these calculations and these studies, I think that this made Thurston to propose the conjecture which was named as geometrization conjecture. And the statement is this: the interior of every compact three manifold has a canonical decomposition, a standard decomposition into pieces which has geometric structures. Now he says that every compact manifold can be decomposed into certain pieces, and each of these pieces will have geometric structures. Okay. So in fact, exactly 8 geometries are there in dimension 3. In dimension 3, he actually proposed that there are 8 different geometries. So this geometrization conjecture was after Poincare conjecture, this geometrization conjecture became a bigger problem, bigger problem which people started handling, people started attempting, and Poincare conjecture became a consequence of this geometrization conjecture. I will tell about it later in one of my slides. Okay, so what we understand till now is that there are exactly 8 geometries in dimension 3. So earlier in one of the slides, I mentioned that there are exactly 3 different geometries in dimension 2, and in dimension 3, there are exactly 8 different geometries. Now we try to understand these 8 geometries. This is very technical part, and if you if some of us do not understand this, do not get disappointed, because it takes a lot of time to understand this. So remember, for how did we define geometries? We took a simply connected space, and we took a group of isometries, and then talked about quotients with the isometric group of the simply connected space. This is how we try to understand the geometries in dimension 3. Now, to describe these geometries, we need to give a simply connected manifold and a group G of orientation preserving diffeomorphism of X with compact stabilizers. So stabilizers Gx are needed to be compact, because otherwise the volume, I mean the size of the manifold will grow, and it will not be in our control. In fact, the result also was about compact manifolds. You know? Okay. So, so based on these stabilizers, actually the geometries are described. So they yes, that is what it says, that they are grouped by identity component of Gx, and up to isomorphism, they are either SO3, SO2, or SO1. So you see these groups, the groups which we are talking about, also are topological spaces. They also carry topology on them. And because it is a group, it must have identity in it. And we are talking as a topological space, we are talking about that component of the group Gx which contains identity. So that is actually identity component of Gx. And up to isomorphism, this identity component, this Gx which we are talking about, is one of these. It is either special orthogonal group uh, of degree 3, special orthogonal group of degree 2, or a trivial group SO1. Okay. Now, first geometry, I will briefly tell about all these 8 geometries. The first of these is spherical geometries. As mentioned, the 3 geometries were immediate, analogous to the geometries in dimension 2, S3, E3, and H3. So spherical geometry is first of these is spherical. In this case, the simply connected part is S3 and G is SO4. So all 3-dimensional spherical manifolds have been classified. An example of this geometry of manifold carrying this geometry is Poincare dodecahedral space. How to obtain this dodecahedral space? You take a solid dodecahedron and opposite faces identify with a 1/10 right-handed rotation. Then you get a spherical geometry on whatever is the quotient space, and the universal covering naturally is S3. Now we come to another geometry, Euclidean geometry. In this case, of course, the simply connected part is E3, and the group is R3 cross SO3. It is the group of Euclidean isometries. There are only 10 non-homeomorphic 3-dimensional Euclidean manifolds. They have also been known, and each of these manifolds are finitely covered by 3 torus. This is also known. The most interesting geometry is the hyperbolic geometry. As in the case of dimension 2, we had seen that it was upper half plane. In this case, it is upper half space. So in R3, you take third coordinate to be greater than 0. That is simply connected and taken as X. In this case, the group we can take as PGL2C of non-singular 2 by 2 complex matrices of determinant 1. up to multiplication by plus minus I scalars. G in this case acts as fractional linear transformation. And if you want an example of, there are numerous examples. One example is obtained by identifying opposite faces of dodecahedron by a 3/10 right-handed rotation. Okay, so in case of a spherical, we identify faces by 1/10 rotation. In this case, we identify faces by 3/10 right-handed rotation. There are some other geometries which are known as product geometries. So this is S2 cross E1 geometry. In this case, the space is S2 cross E1. You can see that this is simply connected space. And in this case, the group, you have to take isometric group of this with product with isometric group of this, that is the group. And till now, there are only 2 examples of compact manifolds with this geometry. Similarly, we obtain H2 cross E1 geometry. In this case, the simply connected part is S2 cross E1, and G will be product of corresponding isometries of this and isometries of this. So a manifold modeled on this geometry is finitely covered by the product of a surface and a circle. So these are some flavors of geometries we are trying to give. Now, the next geometry is denoted by this symbol, SL2R tilde geometry, it is called. It is topologically an R bundle over H2, the upper half plane. As you can see, this is simply connected, and this geometry is carried by the group SL2R, which is universal cover of SL2R and PCL2R. Actually, these groups are looked upon also as topological spaces. They will carry a lot of structures on them, and because of those structures, the geometry is coming. Okay, so example of these geometries are some ciphered manifolds. Another geometry is named nil geometry. This is an R bundle over R2. As you can see, this is simply connected, and it is carried by Lie groups called Heisenberg group. And the groups, these groups, Heisenberg groups, are actually nilpotent groups. Therefore, the geometry has name nil geometry, and its example is a Seifert manifold up to some diffeomorphism. So I have not given technicalities. There is no meaning in giving technicalities. This has to be worked out and understood, and it cannot be done in 1 hour lecture, as many of us know. So the next geometry is named Sol geometry. Sol actually comes from a term solvable, and the group in this case is solvable. We could argue that if the group is solvable, and if it was also nilpotent, or if the group is nilpotent, we can club this with nil geometry, but that is not the case. In this case, the group is solvable, but not nilpotent. You see how complicated the groups become. So the Lie group in this is R3 with operation. What is the operation? X, Y, Z, A, B, C. When they operate together, combine together, they give this. So getting an intuitive feeling of these geometries is somewhat involved. And as we do in topology, everyone actually goes for personal, what we can say, individual feeling of these object. Okay. And in this case, there are examples. There are examples of torus semi-bundle of anoscope type. Some technical term is there. Now, what is more important is that, so let me complete this part. by mentioning that any two closed three manifolds admitting different geometries are not diffeomorphic. So that is to say that all these 8 geometries are distinct. Okay. And the important part is that in fact, one can tell the geometry of manifold directly from its fundamental group. If I know the fundamental group, then we can just tell the geometry, what will be the geometry. So for that purpose, let M be a closed manifold modeled on one of the geometries X. Then if the fundamental group is finite, then the geometry will be, the simply connected space will be a sphere. If fundamental group is virtually cyclic, then it is this. If it is virtually abelian, then it is this, and so on. There are some conditions if it is virtually nil. So all the conditions on fundamental group, except in case 6, in 6 we have two subcases where the space will be either H2 cross R or SL2, the simply connected part using a special linear group. So except in case 6, we will have two descriptions. Otherwise, everywhere we have individual descriptions in terms of fundamental group. If the fundamental group is none of these, then we get a hyperbolic space. Okay. So this is the description. Now coming to another, again, a mention of geometrization theorem. So the geometrization theorem, as mentioned, was proved by 2000, was proved in 2002, and actually the work or the proof of Perelman, all of us know, was based on the earlier work of Richard Hamilton. Hamilton worked using Ricci flow. So this was geometrization. So once geometrization is proved, it was understood that Poincaré's conjecture is also proved. But then how Poincaré conjecture follows from geometrization theorem? I am telling it as a consequence of geometrization theorem. Okay. So the description is as follows. Now, via prime decomposition, we may assume that our manifold M is prime and hence it is irreducible. The group, the fundamental group, is trivial because it is simply connected and does not contain, because it is trivial, therefore it does not contain Z cross Z. So every torus in M will be compressible because it does not contain essential torus. Every torus will be compressible. So therefore, the geometric decomposition becomes trivial. The geometric decomposition which we had talked about becomes trivial. Now by geometrization, therefore, M itself is a geometric, means M actually carries a geometry. Now the only geometry with finite fundamental group is S3. The only geometry which carries finite fundamental group is the spherical geometry. And therefore, M must be a quotient space of S3. Correct? So therefore, M must have a spherical geometry. Now, since M is simply connected, we know the group G is same as fundamental group, so it is trivial. And therefore, when G is trivial, M must be equal to S3. This is how Poincaré theorem is comes as a consequence of geometrization. Is it clear to everyone? Okay.
Very good.
Okay. So I mean, a small description. I mean, it was important to say that yes, Poincaré conjecture now stands proved because the bigger result geometrization conjecture stands proved. Okay. So I talked about some useful references in the previous class. Here are some very important references which are very useful. So one is a note by Alan Hatcher, and there is a PDF book, Geometric Topology by Bruno Martelli. I mentioned about Richard Riley, his paper, which is expository, and it is a personal account of the discovery of hyperbolic structure on some knot complements. Then this is a very, very good paper. This is also exposition, which deals with geometries of three manifolds in detail, starting with geometries in dimension 2. This is in Bulletin of London Mathematical Society, and Thurston's own survey paper, which is three-dimensional manifolds, Kleinian groups, and hyperbolic geometry, which appeared in Bulletin of American Mathematical Society. These are very beautifully written. These, at least these three expository articles, and this second one book. This is a comprehensive treatment of geometry and topology in three dimension, and one can, if one can always refer to them whenever it is needed. Okay, so with this, I think I have completed my part, my lecture, and thank you very much, everyone.
Very good, Ashish.
Thank you, sir. Thank you very much.
Wonderful. Very nicely said.
Yeah. So, any questions? I'll be happy to take questions if there are any.
Yeah, I have one question.
Yes.
So in the definition of Soul geometry, you have
Yes.
written x equal to the trivial, the R2 bundle over R.
Yes.
So is it the trivial bundle?
No, it is not trivial bundle. It is not trivial bundle. So I actually said earlier that these are very technical things, and I just wanted to give a feel that so that the graduate students do not get carried away that it may be something very complicated. I'm just mentioning that it is a bundle. If you want to explore what bundle it is, just go through the references which I have told. Okay. Huh. Yes. Any other question? Yeah. So if there are no questions, maybe I will hand over to the coordinator of this meeting. There will be the next talk will be given by Professor Himadri Mukherjee at 4 p.m. today. I think we should disperse and meet at 4 p.m. for his talk.
Thank you very much.
Thank you, everyone. And if you are interested in my slide, I can pass it over. If I will say, if you are still interested in my slide. Yes.
No, I think it is very good, and quite a few participants may be interested in that.
Yeah.
So
yeah.
it will be good if you pass it on. Very good.
Yes, please. Yeah, someone says here is Gondhali also that I will share slides. Yes, I'll be very happy. But then how to share? Maybe those of you who want, they can send an email, and through email I will send to you. It is in PDF version. Okay, so I will pass it on to you.
Good.
Yes, someone wants video recording. Video recording will be available from YouTube. Video recording will be available from YouTube, and you can access. The link will be shared. Organizers will share. Okay. Yes.
Okay.
Someone wants Khare sir's slides also. Yes. Yes.
I think those who are interested for any particular slide, they may simply send their email address, and
Yeah, yeah.
the
We can
uh,
share. Yes.
and I think the organizer will send them. That's
Yes.
all.
Yes.
Not a
Yes.
big issue.
Okay.
Good.
Okay. So thank you very much.
Thank
And
you very much.
yes.